the two-key test comes in handy because we need, okay, we were significant, but where do those differences lie? What groups are different between each other? It can be essentially thought of as like a whole bunch of little tiny t-tests, but they're done with controlling for all of these other things. And so, right, something that can happen sometimes, although not super frequently, is that you might get a significant overall ANOVA test, but then once you look at your two-key, there's no significant differences between groups. That's because the robustness of your significance of the ANOVA just wasn't that great. Maybe you have too small a sample size, maybe it's just that the effect size is really small, and that just means that you don't have significant differences between each of the groups. Yeah?
What's the difference between the two-key and the Bonferroni?
Oh yeah, so two-key test is looking at the differences between groups in an ANOVA. The Bonferroni is an overall adjustment that's used that we'll talk about in a few minutes in greater depth, but if you're doing multiple comparisons, so say you have like a whole bunch of t-tests that you're doing, then it would adjust your p-value for you. So if you're doing 22 t-tests, I hope you don't, but if you are, then you would do 0.05 divided by 22, and that would be your new critical p-value. So for 22, then you're going to have your new p-value. Your p will have to be less than 0.002 in order to reach significance. That's correct for the type 1 error. Okay, so this is what the output looks like. And if you happen to have had non-parametric, then you'd be using the Games Howell. But two-key. If our variables are beginner, intermediate, advanced, I should have been using the consistent example throughout, sorry about that, but it's just looking at, okay, on our outcome variable, are the differences between beginner and intermediate or beginner and advanced significantly different? So what you do is you just look at the significance and you see that, okay, it's on the cusp, but it's significant. This is significant, this one, and you'll notice that these are the same, right? And that's because both of those are just comparing beginner and intermediate to each other. They're comparing the exact same thing, so it's going to be the same. And these are the same for the same reason, right? And then, so you just know that the significant difference is between beginner and intermediate, beginner and advanced, and that intermediate and advanced are not significantly different from one another. I'll show you what that looks like in an APA report. So there was a statistically significant difference. You provide that ANOVA, that like broad, you first say that was significant. And then a two-key post-hoc test revealed that the time to complete the sexual health education problem was statistically significantly lower after taking the intermediate and advanced course compared to beginner course. There were no significant differences between the intermediate and advanced groups. So that's how you report that. And when you're reporting when you have non-significant results, then you only need to report the p-value. You don't need to report all of the other stuff. Okay. So that ANOVA F-test just tells you there's significant differences between groups. You need to have the post-hoc analyses in order to come up with those multiple comparisons and where the differences lie. Okay, which of the following of these is an assumption of ANOVA? Just yell it out. What was that? Huh?
D.
D, all of the above. Yeah. So the outcome variable has to be normally distributed. Variance of the outcome variable is the same in all groups, or similar in all groups. And the groups have to be independent. Those are the assumptions you need to look out for in order to do the ANOVA. Okay. And the reason that you aren't going to do just 3 pairwise tests, like you could have done that, right? You could have just done 3 separate t-tests and gotten the same results, potentially, But you also potentially could have gotten a type 1 error. So you have this error rate of 5% because you're using a 95% confidence interval. You're using p means less than 0.05. That adds up. That means that you'll have approximately 14% chance of making a type 1 error. So it's just important to think about what are the, and there have been many times where I've like reviewed theses that have used all of these bivariate analyses, and I'm like, you could have done a multivariate analysis here. You should have done a multivariate analysis here. And it's not that it's harder. Yes, you might have interaction effects, and you might have a few things that you need to untangle, but honestly, it's really, once you get the basics of how to do this and how to like, how to read your output, it's not that much harder. In fact, you're giving yourself less work by doing fewer tests and having to report fewer tests, and you're also doing it properly. All right, so we will talk about chi-square now. And chi-square is when you're just dealing with categorical or nominal variables. So no continuous variables here. You don't have any means you're dealing with. You can't see mean differences because they're just categorical variables. It's essentially assessing goodness of fit. How well do these categories fit into these categories? The assumptions, in order to use chi-square, you do need to have independent samples, and you wouldn't be able to do chi-square with couples or with multiple reports from the same person. And they need to be randomly sampled from the population as best as you can discern, similar to what we've been talking about. Okay, so this is where, yeah, we have these chi-square tables that probably your stats class is going to tell you to sit down and look up where the critical value is. SPSS does all of this for you. You don't need to do all of that. So you can do that if you want, but we're not going to here. This is what it looks like, in case you don't remember from your stats class. But I feel like the reason I get like kind of annoyed about this is because I feel like seeing a table like this and having to like figure it out deters people from getting to know stats. It makes it not accessible, and there's no reason to use this when we have output that tells us the exact number that we're looking for. So it's just silly to me, but anyway. So because I mentioned earlier that effect sizes are becoming more and more important, the strength of the association, or the effect size for a chi-square is the phi coefficient, and the chi-square provides these, like, are these things related, but it doesn't provide the magnitude of that, and that's what this allows us to do. And that's on the output as well. Okay, so how do you do this? Chi-square is actually found in descriptive stats and crosstabs. Kind of not what you would maybe expect. You move one variable, it doesn't matter which variable goes into which, but you need to remember which one goes into which. And then you need to click on cells, because otherwise you won't get any output. So if you click on the cells, and honestly, even now, like when I'm doing analyses, sometimes I'll just go through and like click on all of these just to make sure, just to double check. You just check. But you definitely have to click on cells. If you do have an idea of what direction these go in, your IV is going to go into the rows. Always have them show you the observed count. Expected doesn't really matter, you can. In percentages, so you definitely want it across the rows if your IV is in the rows, okay? I will admit, I just click row, column, total. It gives you more information. It can be kind of hard then to make sure that you're getting the right numbers, but it gives you more information. It tells you like within and also between. You can look at it a few different ways. But row is what you need if your IV is in the rows. And then, yeah, that's about all you need. You don't need any adjustments or anything like that. You also need to press on statistics, because otherwise you won't get anything. You're going to choose chi-square, and then the strength of the relationship, in order to get that, you want that Kramer's V. And then you just click continue. And this is what the outcome looks like. The output looks like. So here we're looking at, did they die or did they survive based on gender? And what we find here is that the observed count, so the men, you have the men and then you have the women, and you can see out of the men how many died and how many survived, and then you can see out of the women how many died and how many survived. But it also allows you in that total to look at the combination of those, right? So it'll make, so what you would say here then is, say we're looking at the Titanic, most men on the Titanic died, 80.2%, versus most women survived. So you're getting that by looking at percentage within each gender, okay? So within women, percent within women, 71% survived, 28% died. Within men, 80% died and 20% survived. Okay? And you can do a few like checks on yourself with that by just making sure that things are adding up to 100 and making sure that you use the right number.
Where does the expected count come from?
The blue highlighted the expected count. So that is related to, let me think for a second. So if you look at the total, the expected count is going to be, let me just make sure that this is adding up properly. I don't pay attention to it, so. Yeah, so it's just providing the actual number rather than the number within each section rather than the count of like women who died compared to women who survived. And so if you look over to the totals, you'll see like these totals, they're the same for both of those. I don't use that. I don't use it ever. So. Yeah. And chi-square can be confusing, especially if you do end up clicking row, column, total like I do. You really then have to like make sure that you're paying attention to what you're pulling. And you're looking at this to see if it's significant. So this provided you the numbers you needed, but it did not tell you if there were significant differences between the groups. This is where you get the significant difference between the groups because we chose chi-square. This tells us that it is significant, and the relationship is significant. Chi-square, degrees of freedom in parentheses is equal to p is less than 0.001. Okay? Any questions about that? All right.
When you report p on that,
Yeah.
is that just p equals point?
So because the p value here is 000, we don't know the rest of the numbers. They're not reported. It only reports up to 3. So it's most accurate in this case to say, rather than rounding. Because it's never going to be equal to 0.00. Yeah. And so you can use this if you have more variables. Like in this case, we're just comparing 2, right? But you can enter like a whole bunch in the rows and a whole bunch in the columns. And in that case, you would use the Kramer's V to look at that effect size. But if you've just got 2, then you're looking at this range, and this is how you can tell the effect size. And you'd want to make sure that you're reporting these with your results so that you know what the actual impact is. So gender had actually quite a large effect on chance of survival on the Titanic. Because the value is 0.5 above. This is just showing you this again. So gender was not the only factor. Social class was also significantly related. Oh, that's what this was showing, yeah. social class, so upper, middle, and lower. Social class is also related, and this is just how it would be written up. And then you can see where the 61.5%, where the 40.7% comes from, and that it was a moderate relationship because of frequency. So this is the sort of thing, I'm going to give Dr. Irwin these slides. This is the sort of thing where if you do the test, just pull these up and like just follow along with it. It's kind of, as I said, like this is why it's hard to do these things if you're not doing the actual research, because you're never going to fully understand how to do it until you actually sit down at a computer and do it. Okay, so this is our Bonferroni correction. And this adjusts the P by the most conservative amount. It's a good thing to do if you have those multiple comparisons like I described. 2P automatically does an adjustment. So you don't have to do an adjustment in addition to 2P. 2P does this adjustment when it's comparing those multiple groups on its own. The KHP test, which is the alternative to the 2P, also does that. So with the Bonferroni test, as I just mentioned, if you have 5 tests, then your original alpha was 0.05, your new alpha is 0.10. Does that make sense? So just if you're doing multiple comparisons, if you're doing a whole bunch of different tests, correct with the Bonferroni of the same. If you're doing a whole bunch of the same tests, correct using a Bonferroni adjustment. And the computer calculates your 2P. So the computer does not calculate Bonferroni for you. This is one that you do need to know how to divide P 0.05 divided by the number of tests. It's very simple at least. 2P and KHP are both corrected already for you, but they are less conservative than the Bonferroni adjustment. So I talked to you about those pretty basic tests, right? Like the main ones of t-test, ANOVA, chi-square. Once you get into multivariate and you need to increase your number of variables that you're using, then you're going to get into some of the regression stuff if you're using continuous outcome variables or continuous predictor variables. Some of these are discriminant function analysis. I'm not going to talk in depth about these. I'm just going to let you know that they exist and that they are sort of the next step in stats beyond what we talked about today. And what discriminant function analysis